If you look closely at the ramp of any major airport, you'll notice an interesting pattern. On modern long-haul airliners like the Airbus A350 or the Boeing 787 Dreamliner, the massive turbofan engines are mounted directly under the wings on special pylons. But if you shift your attention to the business aviation area, the picture suddenly changes. Private jets, such as the Gulfstream G650 or the Bombardier Challenger 350, almost always place their engines at the rear of the fuselage. Their wings remain completely clean, without engines hanging underneath. And if you look at aircraft from previous decades, you'll notice yet another unusual layout. Some airliners even had 3 engines, like the Boeing 727 or the McDonnell Douglas DC-10. So the question is, why do airplanes use such different engine layouts? The answer is simple. In aviation, almost nothing is random. Even a small change in engine position can affect an aircraft's balance, stability, and flight behavior. Every configuration is the result of a compromise between aerodynamics, structural design, safety, and operating economics. To understand why engines are placed where they are, we first need to look at what the engine actually does. A jet engine produces thrust, the force that pushes the aircraft forward. As the airplane accelerates, the wings interact with the airflow and generate lift, which keeps the aircraft in the air. In other words, the engine doesn't lift the airplane directly, it simply provides the speed required for lift. But thrust itself isn't the only thing that matters. How that thrust is distributed is just as important. If one engine fails, the thrust becomes asymmetric, and the aircraft will start yawing toward the failed engine. Pilots counter this using the rudder. That's why airliners are designed to remain controllable even after losing one engine. And this is exactly why engine placement matters so much. Engines can't simply be installed anywhere. Their position directly affects the aircraft's balance, stability, and overall safety. The first challenge, center of gravity. For an airplane to fly safely, it must be properly balanced. A simple way to think about it is like a giant seesaw, where the wing acts as the pivot point. 2 key factors determine this balance: the center of gravity and the center of lift of the wing. The center of gravity is the point where the aircraft's total mass is effectively concentrated. For stable flight, it must sit slightly ahead of the center of lift. This creates natural longitudinal stability. If the nose moves up or down, aerodynamic forces tend to bring the aircraft back to its original position. Now add engines to the picture. Modern jet engines are some of the heaviest components on an aircraft. For example, the Rolls-Royce Trent XWB engine used on the Airbus A350 weighs several tons. If engines are placed too far from the center of gravity, for example, far back in the tail, the aircraft's balance starts to shift. The airplane would naturally tend to pitch nose up, and engineers would have to compensate by lengthening the fuselage or enlarging the tail surfaces. That's why aircraft designers follow a simple principle. The heaviest components should be placed close to the aircraft's main load-bearing structure. On most airliners, that structure is the wing, the part of the aircraft designed to carry the largest loads during flight. Why most airliners mount their engines under the wings. The wing is one of the strongest structural parts of an aircraft. Inside it is the wing box, a rigid structure made of spars and ribs that carries the main loads during flight. By mounting the engines under the wing on pylons, engineers use this strong structure as a support for a multi-ton power plant. Since the wing is already designed to handle enormous loads, it can carry the weight of the engines without requiring major reinforcement of the fuselage. In fact, engines mounted under the wing can actually help the wing structure itself. In flight, lift tends to bend the wings upward. The weight of the engines pulls downward, partially counteracting that force. This reduces the bending load at the wing root and allows the wing structure to be lighter. Another reason is the size of modern engines. To improve fuel efficiency, modern turbofan engines use a high bypass ratio and very large fans. The larger the fan diameter, the more efficient the engine becomes. As a result, Modern turbofan engines have grown significantly in size, and mounting such large engines in the tail of a large airliner would be far more difficult from a structural standpoint. There are also practical advantages. Most airliners store their main fuel supply inside the wings in so-called wing tanks. With engines mounted under the wings, the fuel lines are shorter and simpler. In some emergency situations, fuel can even flow to the engines by gravity. Maintenance is another factor. Because the engines are relatively close to the ground, technicians can inspect and service them without complex lifting equipment. This reduces turnaround time and lowers operating costs for airlines. But the underwing layout also has drawbacks. Despite its advantages, mounting engines under the wings is not a perfect solution. One limitation is ground clearance. Modern engines are becoming larger, so engineers must carefully design the landing gear height and engine nacelle shape to maintain a safe distance between the engine and the ground during takeoff and landing. A low engine position also increases the risk of FOD, foreign object damage. Stones, ice, or debris from the runway can be ingested into the compressor and damage the engine blades. For this reason, runways are carefully cleaned and pilots avoid power settings that might kick debris into the airflow. Another issue appears if one engine fails. Because the engines are located far from the aircraft's centerline, the remaining engine produces a strong yawing moment. To counter this, airliners require a large vertical stabilizer and a powerful rudder. Engine placement can also affect pitch behavior. When engines are mounted slightly below the aircraft's center of gravity, changes in thrust create a pitching moment. Increasing thrust tends to raise the nose, while reducing thrust tends to lower it. This effect is known as thrust-pitch coupling, and pilots account for it when managing power. In the end, the underwing configuration is not perfect, but for large passenger aircraft, it remains the most effective compromise between structural design, aerodynamics, and operational efficiency. Why some aircraft mount their engines in the tail. But if the underwing layout is so effective, why do some aircraft still place their engines in the tail? Although most large airliners use engines mounted under the wings, the rear engine configuration also offers several advantages. That's why it's commonly used on business jets and regional aircraft. One of the main benefits is a clean wing. Without engines and pylons attached underneath, airflow over the wing is smoother and more uniform. For smaller aircraft, this can provide a noticeable aerodynamic advantage. Another important factor is protection from debris. Tail-mounted engines sit much higher above the ground, which greatly reduces the risk of ingesting stones, ice, or debris from the runway. This can be especially important for aircraft that frequently operate from smaller, regional airports, where runway conditions may not always be perfect. Engine placement also affects cabin noise. Much of the noise from a jet engine comes from the exhaust jet and the turbulent airflow behind the engine. When the engines are positioned behind the passenger cabin, a large portion of that noise is directed away from the fuselage. As a result, the front section of the cabin can be noticeably quieter. One reason this layout is popular in business aviation, where passenger comfort is a priority. Another advantage is wing design. Without engines mounted underneath, engineers can use more of the wing's trailing edge for flaps. This increases lift at low speeds and helps the aircraft take off and land on shorter runways. There's also a practical reason. Many business jets are equipped with built-in stairs known as an air stair. For the stairs to be convenient and not excessively long, the fuselage needs to sit relatively low to the ground. In this configuration, there often isn't enough space under the wing for large engines, so they are moved to the rear of the aircraft. In some cases, tail-mounted engines even allow aircraft to reverse away from the gate using thrust reversers. Aircraft such as the McDonnell Douglas MD-80 or the Boeing 717 have occasionally used this technique, allowing them to back away from the gate without a pushback tug. However, the rear engine configuration also has its engineering challenges. First, the fuel system becomes more complex. The main fuel tanks are still located in the wings, so fuel has to travel through longer fuel lines to reach the tail-mounted engines. Second, the layout affects aircraft balance. Since the engines sit behind the wing, they can shift the aircraft's center of gravity aft. Engineers must compensate by carefully distributing equipment and mass throughout the fuselage. Engine placement can also influence pitch behavior. If the engines are located above the center of gravity, changes in thrust can create the opposite pitching effect compared to underwing engines. Increasing thrust tends to push the nose down, while reducing thrust can cause the nose to rise. Pilots account for this behavior when managing power. Finally, aircraft with tail-mounted engines often use a T-tail configuration. This places the horizontal stabilizer high above the wing and engines, where it can operate in cleaner airflow. But T-tails introduce a well-known aerodynamic risk called deep stall. At very high angles of attack, the disturbed airflow from the stalled wing can blanket the horizontal stabilizer, reducing the effectiveness of the elevator. In extreme cases, this can make recovery difficult. To prevent this, many aircraft with T-tails are equipped with automatic protection systems, such as a stick pusher, which forces the control column forward if the aircraft approaches a dangerous angle of attack. In the end, the tail engine configuration, like the underwing layout, is a compromise. It offers clear advantages for smaller aircraft, but it also requires additional engineering solutions to ensure stability and safety. But there was also a third layout, one that briefly dominated long-distance aviation, known as tri-jets. These aircraft appeared during the 1960s and 1970s when jet aviation was expanding rapidly, but engine reliability was still lower than it is today. At the time, safety regulations limited how far twin-engine aircraft could fly from the nearest diversion airport. If one engine failed, the aircraft had to be able to land relatively quickly. This created a serious limitation for long-distance routes. For transcontinental and especially transoceanic flights, airlines needed greater redundancy. As a result, aircraft were typically designed with either 4 engines or 3. Tri-jets became a compromise between safety and efficiency. 3 engines provided additional redundancy in case of an engine failure, while keeping the aircraft lighter and more economical than 4-engine designs. One of the most famous examples was the McDonnell Douglas DC-10, a wide-body aircraft designed for long-haul flights. It was later followed by the more advanced McDonnell Douglas MD-11, which became one of the last large passenger tri-jets ever built. However, as aviation technology advanced, the tri-jet configuration gradually became obsolete. Modern turbofan engines became far more reliable, powerful, and fuel-efficient than those of the early jet age. At the same time, aviation regulations evolved. New standards, known as ETOPS, allowed twin-engine aircraft to operate safely on long routes far from diversion airports, thanks to improved engine reliability and better monitoring systems. Once those restrictions were lifted, the advantages of tri-jets quickly disappeared. Aircraft with 2 engines were simply easier to design, lighter, and cheaper to operate. Airlines no longer needed to maintain 3 or 4 engines when 2 could do the job just as safely. Looking at the history of civil aviation, one thing becomes clear. Engine placement is never random. Every configuration is the result of a careful compromise between aerodynamics, structural design, safety, and operating economics. That's why most modern airliners use 2 large engines mounted under the wings, while business jets and many regional aircraft still prefer tail-mounted engines. In aviation, every design choice is the product of precise engineering and decades of experience. And it's exactly these engineering decisions that allow today's aircraft to safely transport millions of passengers around the world every day.